Today we're going to be talking about the chi-square goodness of fit test. We're coming back to this. This is 11.1b. We started this the other day in class, and now we're on our online period. I do want to introduce myself for anybody that stumbles across this video somewhere else. I'm Mr. Moon, and this is my AP Stats course. We are going out of the practice of statistics, Chapter 4, and this is our Chapter 11, Section 1b. On the chi-square goodness of fit test. So we're going to start with an example on birthdays. And what I mean by birthdays is literally the days of the week. So the thing you might expect about this, and this is another case of an expected distribution versus what we observe in our sample, we might expect that births are kind of evenly distributed across days of the week. For example, the number of births on a Sunday would be the same as the number of births on a Monday. Well, we're looking at the data here from a random sample of 140 births from local records in a large city. And what we're asked is, do these data give significant evidence that local births are not equally likely on all days of the week? Some of you might notice that this is actually perfect context for a chi-square goodness of fit test, because the goodness of fit test basically says, take a distribution, look at the observed data, calculate your statistic, and see how different we are from what the claim is. In this case, here's the claim. Null hypothesis, or the claim, is that birthdays in this local area are evenly distributed across the days of the week. The alternative hypothesis is birthdays in this local area are not evenly distributed across all days of the week. So the null hypothesis can also be written as, that the proportion of births on each day is 1/7. So you could, if you wanted to, and I'll highlight this if I can find a way to do that. I'll just, always point it. So we can also write the hypotheses like this. We can have this P of sun equals P of mun equals P of 2s, and so on, and all of these equal 1/7. Of course, the alternate hypothesis there is at least one of the proportions is not 1/7. When you think about it, it really would need to be at least two proportions that were off, but I'll not split that here today. And we're going to use an alpha level of 0.05. So basically the claim here is that there's an equal proportion of babies born on any day of the week, and we're going to go in and see how much our evidence disagrees with that claim. First thing to do is check our conditions. We need to check the conditions before we can do this chi-square goodness of fit test. So we need to look across random, large sample size, and independent. First of all, random. The data came from a random sample of large births. I will actually mark. It says this right here. I'll circle that. We have a random sample of 140 births. So that one is met. Now, assuming the null hypothesis is true, then we'd expect 1/7 of the births to occur on each day of the week. We need to go through and find an expected count now for each day of the week. An easy way to do this is just to take this probability 1/7 and multiply by the total, which is 140. That actually gives us 20 births per day. And remember that we need that expected count to always be bigger than 5. So here we can see pretty clearly that 20 births per day will be bigger than 5 on any given day. So we have a large enough sample size. And I want to remind you guys that we have to do that math with the expected counts. We have to check that condition with the expected counts and not the observed counts. That's a really common mistake. Okay. Finally, independence. We are sampling here, so we're going to have to check the 10% condition. A couple things we want to go through, though. First of all, individual births in the random sample should occur independently. This basically means that one baby being born on a Wednesday doesn't affect when another baby is born. This should be true except for twins, so we'll take that as mostly good. We are sampling without replacement, so there need to be at least 10 times the sample size, or 1,400 births. That math is shown right down here in the local area. This was said to be a large city, So it seems reasonable to assume, I don't know exactly what our time period is, but it seems reasonable to assume that as long as we looked for a couple of days or weeks, there would probably be like 1,400 births in the local area, since this is, after all, a large city. So I'm going to switch back, let's see, switch off my pen. So that basically walks us through setting up the hypotheses and checking the conditions. Now the next thing we're going to do, of course, is actually do the math. And today I'm going to show you how to do all this stuff pretty heavily on the calculator. So the first thing I want to do is, well, let's see. Okay, so they don't actually give us the numbers there. So I'm going to stay on this slide for a moment so that we can actually put the data into the calculator before we move on to the next thing. So I'm going to do this on the Inspire, and then we'll do it again on the 84. Might need to move my Inspire a little bit so I can actually see what's going on. Well, we'll get to that. So I'm going to go into the menu. I'm going to add a lists and spreadsheet page so we can actually save our data. Now I'm going to put in two columns here. I always want an observed column and an expected column. Oh, can't call it that. So let's call it obs and x. And we'll move this to the side a little bit. So on Sunday, we observed 13 births. On Monday, we observed 23. Tuesday, 24. Shift this back. There we go. We got 20, 27, 18, and 15 there's Saturday. Now, expected counts here are really easy. We've got 20, 20, 20, 20, 20, and 20, and 20. Okay? So at this point, I want to show you guys how to do that same step on the 84, just so we're all on the same page. So let me jump over to my 84, which I have now, so that's cool. And we're going to go in here, and we're going to go to Stat and Edit. All right, let's see if I remember how to use an 84. So again, we're going to put in the 13, we're going to put in the 23, we're going to put in the 24. I'm going to move the calculator because I can't see all my data. We'll put in the 20, we'll put in the 27, 18, 15, and we're going to go over to L2 now. And remember, every expected count is going to be 20. So we can put 20, 20, 20, 20, 20, 20, 20. Alright, so that brings us to the point where we actually want to start the next step. So I'm going to switch back to the Inspire so you guys can see how we actually do the test. First thing we want to do, open up a new page. This is the way I would do it. There is another way to do it. But let's open up a new page. We'll go to Calculator. We're going to go to Menu, Statistics, Stat Tests, because we want to do a chi-square goodness of fit test. And hey, look, chi-square goodness of fit test. Cool. Our observed list, we were smart. We called it OBS. Our expected list is X, short for expected. Now, degrees of freedom. This is one that you might not remember how to do. Remember in the last chapter, degrees of freedom was always n, meaning sample size, minus 1. Here in the chi-square chapter, for the goodness of fit test, it is n, the number of categories, minus 1. So if we look at our data again, let me jump back there. How many categories are there? Well, there's Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. That is 7 days, 7 categories. Okay, so we are going to use 6, which is 7 minus 1, to be our degrees of freedom. And that actually gives us our chi-square goodness of fit test. It is giving us a chi-square statistic of 7.6. It is giving us a p-value of 0.268897, and it is giving us the degrees of freedom, which we put in as 6. So that would be the information you'd want to record when you report doing your chi-square goodness of fit test on the calculator. By the way, when you're on the AP, it is appropriate to do this step on the calculator. You should do a couple things. It's good to name the test by name, meaning chi-square goodness of fit test. It's also good to list out the formula, which we're going to look at in a minute, but is that chi-squared equals observed minus expected squared over expected. That will help a lot. Then you can show the chi-square statistic, the p-value, and the degrees of freedom that you use for the test. And then we can analyze the p-value, which we're going to do on the next slide. before we move on, I want to repeat this process on the 84 so that anybody with the 84 knows kind of what they're doing here. So let's switch back to the 84. We've got our lists entered L1 and L2. L1 is our observed, L2 is our expected. So we can actually quit out of the stat edit menu, and we're now going to go to stat. We're going to move over to tests. We're going to go down, 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 down. Keep going down. I know it's here somewhere. Alright, we got the chi-square goodness of fit test. So we're going to observe L1, expected L2. Degrees of freedom here, we talked about this, are 6. And, we can actually draw this? That is cool. So, the 84 will actually, as part of its function here, quickly visualize the chi-square goodness of fit test. So this gives you a nice little sketch, which you could reproduce on the AP test. I am going to look to see if I can find a way to do this on the Inspire, because this is really, really neat. And if any of you find a YouTube video on how to do this on the Inspire, please send it my way so I can make sure it gets out to everybody. But this gives you the same information we saw from the Inspire. The chi-square statistic was 7.6. The p-value is 0.2689. Now, p-value of 0.2689, that is going to be non-significant, meaning not statistically significant, meaning, we'll get to this on the next slide, we're probably going to fail to reject. So let me just walk you through the math. And by the way, this is the formula that I think is really important right up here. Chi-square equals sum of observed minus expected squared over expected. If you're going to write down that you're doing a chi-square goodness of fit test on the calculator on the AP exam, I would recommend you write down this formula. It'll help a lot. Now, if you want to do it out by hand, here's the math. 13 minus 20 squared over 20. 23 minus 20 squared over 20. Notice we're always going to be subtracting 20, squaring that thing, and then dividing by 20, because 20 is always the expected count. Now, lots more babies born on, or lots fewer babies born on Sundays. Kind of interesting. Let's see, Monday, Tuesday, Wednesday. Lots more babies born on Thursdays. So more babies on Thursdays, fewer babies on Sundays, just based on this. And that gives us a chi-square of 7.6. Now, when we run the math on that, as we saw on the calculator, the p-value is like 0.269. Now, that is way above 0.05, which is our alpha level. So, because the p-value of 0.269 is above or greater than alpha of 0.05, we fail to reject H0, their null hypothesis. These 140 births do not provide enough evidence to say that all local births in this area are not evenly distributed across the days of the week. So we cannot conclude that local births are not evenly distributed across the days of the week. I know that's a double negative. I know there are some of you out there thinking, well, that means that local births are evenly distributed. We have not proved that. We just have failed to disprove it, which is a different thing. Okay, let's move on to our next example here. And I think this is the one with the plants. Yes. All right, so we're going to look at inherited traits here. Biologists want to cross pairs of tobacco plants having genetic makeup with the dominant and recessive gene. So each offspring plant will receive one gene for color from each parent. Now, if the resulting plant has dominant, which I think is homozygous dominant, then they're going to be a green tobacco plant. If the plant gets dominant recessive, they're going to wind up yellow-green, and if they're double recessive, they're going to be albino. Now, the Punnett square suggests that we should see 25% green, 50% yellow-green, 25% albino. Some of you are in APIB bio, some of you are not. Hopefully everybody can kind of follow my logic there. The big key part of this is that half of the plants should be yellow-green, a quarter should be green, a quarter should be albino. That's really what you need to take away. So to test this, the biologists are going to produce 84 offspring from these yellow-green parent plants. Now, of these 84 offspring, 23 plants were green, 50 were yellow-green, and 11 were albino. So right off the bat, we notice that this is not perfect because the 11 and the 23 don't match. They should, they don't. So we know that something's off. The question is, do these data differ significantly from what the biologists have predicted? And what we're going to do is carry out a chi-square test at the alpha equals 0.05 level to help answer this question. So let's get into it. We want to perform a test of this null hypothesis, which is that the biologist predicted color distribution for tobacco plant offspring is correct. The other way to put that would be P of green equals 0.25, P of yellow-green equals 0.5, and P of albino equals 0.25. The alternative hypothesis here is that the biologists are wrong about at least one of those stated proportions, or you could say their predicted color distribution is not correct. We're going to use an alpha of 0.05. And before I do anything else, I'm actually going to go back into my calculators. I'm going to clear out some of the old data, and I'm going to put in some new data. So let's jump back over there. We'll go to the Inspire first. And we're just going to go here and kind of wipe out. Let's see, can we just clear this whole column? Yeah, we'll just clear these whole columns. And we'll just replace the observed and expected counts. So here's where things get a little tricky. Observed is easy. We've got 84 offspring, 23 green, 50 yellow-green, 11. So we've got 23, 50, 11. The question is what we're expecting. So we have 84 plants total. 25% of them, which we can model like this, should be green. So if we do that math, it's 21. Now, 84 plants times 50% is going to give us our yellow-green number, which is 42. And 84 plants times 25% again should give us 21. Notice that what I'm doing there is I'm actually typing the equal sign followed by my little formula here, which is, in this case, 84 times 0.25 to get 25% gives 21. So that's a nice little trick for getting the expected counts. We'll look at some more tricks for that as we go forward. So let's do this in the Inspire all the way first, and then we'll go over to the 84 and do it all the way through as well. So we're going to do a new chi-square goodness of fit test. I'm going to get rid of the old one. There we go, gone. And we're going to go back into menu, back into stats, back into stat tests, chi-square goodness of fit. Observed is obs again, expected is x. Now in this case, we have three categories, yellow, green, green, and albino. So our degrees of freedom is 2. 3 minus 1 is 2. We're going to run that. Now, in this case, the chi-square statistic is 6.476, which is about 6.48. And our p-value is 0.039. Ooh, this looks significant to me. Okay, let's double check the math over here on this end. So here's our state step. We already talked about that. Let's look at the conditions. For randomness, the data came, that's a typo. The data actually came from a random sample of plants, not local births, unless the hospital is now monitoring plant births. So for the large sample size, we actually did our expected counts. Those came out to be 21, 42, 21. All of those are bigger than 5, so we're good in the large sample size case. And by the way, drawing that table is a really great idea as you go into this, because it kind of just shows the greater what you did with your data. For the independence case, individual offspring inherit their traits independently from another, right? So one plant doesn't affect the other one. And since we're sampling without replacement, we would need at least 840 tobacco plants in the population. That seems reasonable to believe, considering we're probably drawing from like a large kind of factory farm sort of thing. Unless this is a very small farm, it seems like 840 tobacco plants is pretty reasonable. So let's look at the do phase. We're going to start by calculating the test statistic, which we know should come out to be, I think, about 6.47. And if we go through this math, again, we're writing out the formula. And this, here, let me show you the part you should actually write on the test, assuming you did this on the calculator. You should make sure that this formula is written down, okay? And this is for a chi-square goodness of fit test. Write this formula, and then you can, if you want to, you can show plugging the numbers in, right? So 23 minus 21 squared over 21, 50 minus 42 squared over 50. This should actually be a 42 on the bottom. That's another error on my part. And 11 minus 21 squared over 21. That should give 6.47. But if you don't have time to write that middle step, then I would skip it. I need my pointer back. There we go. So let's look at the area here, and I'm actually going to bring up the 84 again so we can visualize how to do this and see how to do this in the calculator. Okay, so let's go back to our stat table. We're going to go to stat. We're going to go to edit. And let's just use L3 and L4 for this. So if I remember correctly, let's see, 23, 50, and 11 were our observed counts. 21, 42, 21 were our expected counts. And this is an L3 and L4. I'm reminding myself of that so that I can now go do the test. So let's go to stat. We're going to go over to tests. Remember, we're going down. I think it's like B or something. Oh, past B, I guess. It is D. Okay, we're going to go to D. Chi-square goodness of fit test. Here we need to use our list variables. So you can actually click vars here. Just kidding. You can't do that. We actually need to go to second stat, which will bring up the list. You can go to L3. And then if you go down, and go again, second stat will give you the list menu. Go down to L4. Boom, we're ready to go, except degrees of freedom are not 6. They are 3 minus 1, which is 2. Let's do this one in... Oh, I can't change the color? That's too bad. Alright, we're going to draw this. Okay, as you can see, that's a much smaller area than the last one. The curve is also really different, which is a weird feature of chi-square tests. So here our chi-square statistic is actually lower than last time. It's 6.476, which is about 6.48. And we have a p-value of 0.0392. So we actually do have a low enough p-value that we're going to reject the null hypothesis. So because the p-value 0.0392 is less than alpha equals 0.05, we are going to reject the null hypothesis. We have convincing evidence here that the biologist's hypothesized distribution for the color of tobacco plant offspring is incorrect. Cool. So the next thing we're going to do is we're going to follow up, because we'd like to know which of the colors actually threw us off the most in this. What I mean by that is we're going to examine which categories of the variables show the biggest deviations between the observed and expected counts. We're going to look and see like which components are really adding the most to this chi-square statistic. So what we're going to see here, and you can actually see this math down below, is that for green, we're not off by that much. It's 2 plants, which 2 squared is 4, divided by 21 gives us, a very small number. In the yellow-green, we're actually off by about 8, which 8 squared is 64, but we're dividing by 50, so again, it's 1.5, which is a lot bigger, but not huge. The albinos. The albino observed count is way under the expected count. It's 10 under. So when we do 11 minus 21, that's negative 10. We square that, that's 100. Divided by 21 is almost 5. So that's actually driving most of the chi-square statistic here. This 4.7 is the majority of this 6.4. So all this is showing is that you really can follow up with these chi-square examples and see which component or which category is really causing the magnitude of the chi-square statistic to be larger or smaller. In this case, obviously, it's pretty big because we did get a significant result. Okay, so that's actually where we're going to stop here. I'm reminding you guys that we're using this chi-square goodness of fit test for a one-way table. It's really good at testing this null hypothesis that a categorical variable has a specified distribution. And it's comparing observed counts to expected counts using this formula, which I'm just going to use the laser point to highlight, this formula down at the bottom. So I posted a couple videos on this. I'm going to post this video of the stream. I might trim down the beginning where I wasn't talking a little bit at the beginning. But you guys should have plenty of resources to go off of to finish your notes and refer back to. I'm going to stop here because this has been about 25 minutes. Thank you for everybody who watched. Please feel free to reach out with me for any questions, anything I can clarify about chi-square goodness of fit. And section 1, you guys are going to be starting your review exercises, I think tomorrow. That first round of review exercises I would try to finish by Wednesday's class, and then I would just kind of keep moving forward. The assignments are going to pop up in Google Classroom, so you should be able to just knock those off. Anyway, guys, if you were able to tune in, thanks so much for watching, and hopefully this taught you enough about chi-square goodness of fit.